peek every once in a while and
Yeah.
make sure that it's all jacked and crooked,
So you're gonna
but
focus
whatever.
on those two boards?
Yeah,
Don't go over there, because
I
you will
won't.
not be in the picture
I
at all.
won't. I won't. Thank you so much. Okay, let's do this thing. All right, are there any questions that people have? No?
Well, it depends.
What's that?
Well, it depends. We got a lot of questions about everything, but specifically,
Yeah. Well, I was like, did you go over and there's stuff, stuff you had issues with?
What are some of the main things you're gonna like focus on the exam? Like at least
I mean, in all honesty, everything's fair game. Everything, if I put it on the board, and you don't even, it's not even vague, right, in my class, because I don't do PowerPoints, and then, if I wrote it up there, it's fair game. Natural tendency is, if this is the things that I focused on for these 3 exams, most likely that'll be the things that I focus on for the final as well, okay? So, the bulk of the exam is these things. But again, it won't be these exact problems, okay? So, I know, let's do that exercise. Okay, so, maybe that's not a good one to do. What do you guys feel worse on, old stuff or new stuff?
new stuff.
New stuff? Yeah.
I think the last exam new stuff.
Yeah.
Can you go to the second problem on the last exam?
Yeah. Hopefully. Oh, yeah. So this was just a matter of seeing that we learned essentially 3 different ways to do dihydroxylations. Dihydroxylations is a fancy name for taking an alkene, getting rid of the double bond, and putting 2 OHs on each of the carbons of what was formerly the alkene. Okay? So, I don't think it threw anybody, but in the end, I probably wouldn't use a benzene ring right there again. I don't know. It didn't seem to mess anybody up, but and I think I referred earlier that benzenes have extraordinary stability, and most alkene chemistry does not affect benzene rings. Okay, so if you, well, the most direct way, okay, to do a dihydroxylation is dihydroxylation reagents, okay? And we learned 2 different kinds. Okay. And those dihydroxylation reagents deliver both hydroxides with syn addition. Okay. So essentially, and the 2 reagents possible are potassium permanganate. Okay, you need some water in there and some hydroxide. Or, okay, and either of these were accepted, osmium tetraoxide, and then followed by a second step of hydrogen bisulfite. Or I'm sorry, just sodium bisulfite, rather. Okay, and water. Okay. So essentially these reagents, they just land on the alkene, okay? And they bring sort of both hydroxyl groups with them. Okay, we didn't really go over the mechanism for that reaction, and I don't want to introduce new mechanisms at this point. But essentially 2 oxygens come in. This double bond goes out to 1 oxygen. The other oxygen makes his connection. But I think you can just sort of naturally see that, I mean, what reagent, unless it had a big long chain with OHs on opposite ends of the chain, what reagent could possibly come, land on one side and deliver 1 OH, and then somehow reach around to the other side and deliver the other OH? Okay, so any reagent that reacts with an alkene, he's probably initially going to have to bring in both groups with syn addition. Yeah?
Well, that was partially right.
What's that?
I was partially right. I knew there had to be water in there.
Oh, okay. Did you, yeah, I gave everybody a little bit of credit for water. Water is sort of the least important of that, but you got some points. By the way, hopefully you added up all your points and made sure my addition's correct, or looked at the key. You know, double check everything. I love to give points that I missed somehow.
Are the numbers that you write
Just-
in red at the bottom, are those numbers that you're taking off, or, so I was a little confused.
So like if at the end of the page.
Depends on the exam.
Oh, great.
Depends on the exam, yeah.
Okay.
What I do it the fastest way possible. With exam 3, the last exam, I think all the numbers are points given. Those are the points I gave.
Okay.
Okay. Okay, so I mean it's as simple as all that. That's how you get syn dihydroxylation. Okay. Now the trickier part was how you got anti-hydroxylation. Okay. And you sort of, you know, you really probably needed to know the stuff pretty cold to get this one. So MCPBA, step 1, and then step 2, the best way to do it would be sodium hydroxide and water. Okay. So after step 1, what we have is what? What does MCPBA do? Which, by the way, is metachloroperoxybenzoic acid. What does that do?
The OH detaches from the imaging.
Well, if you're describing the mechanisms, that's kind of what it does. Yeah, sort of what it does. But in terms of what functional group it gives you at the end, what final product you get, any ideas? No. This definitely explains why this problem is hard. That gives you an epoxide. Okay. And it could give you either. Okay. But it'll give you that. Okay. And then the hydroxide part, the second part, okay, comes in, and essentially it's an SN2 reaction. It's going to attack one of the carbons of the epoxide. Those bonds from carbon to oxygen are weak because of why? I thought you told me in class.
I don't know.
I totally just called you out. I apologize. Yeah, ethers are typically fairly stable, but these ethers are not that stable. So you can attack one of these carbons and the oxygen will actually let go of that carbon. Behaves like a leaving group. Okay. Anybody, any ideas why? Why is that ether reactive and all other ethers are totally unreactive? We use them as solvents. We do all these chemistries in them, and they're inert to the reactivity. I'm sure you did.
Maybe I did. Maybe I knew it way better.
Just take the credit. Just yeah. Oh yeah.
I knew it better.
Angle strength, right? It's a. Remember that I screwed up because I don't have my triangles. We decided that this is an equilateral, not an isosceles, because isosceles, yeah, an equilateral triangle. So each angle is 60 degrees, yeah? And a carbon normally wants what for its hybridization of an sp3 carbon? 109.5. So that's a big derivation from what it normally likes. That weakens these bonds, okay? So anyway. So essentially it does an SN2 reaction on either of those carbons, and it didn't matter, you get the right answer no matter which one you used. So what do we know about an SN2 reaction? What are some of the characteristics of an SN2 reaction? Backside attack. So it can't, the way I've drawn it, this epoxide is sticking in our room, yeah? So the hydroxide has to come from the other room, it can't come from the same side. So if it comes from that one, it means it's still back in that room. This bond breaks and pops up there, okay? And then you'd actually, technically you'd need a third stage. I wasn't even looking for that from you guys, where you added in some acid, because right here you're just going to have the hydroxide. Okay. Now note, when you attack an epoxide, you only get inversion at the carbon that got attacked. Okay, you don't get inversion there. That's I sort of liken that to it's pinned down and you just sort of release it. Yeah. That was all there was. Does that make sense? Was it just the second? Well, I guess, yeah, this problem didn't go well. The problem didn't go well. Not a lot of people got that right. Hardly any got that right. Okay. All right. I got an idea of an exercise I want to do, unless you guys got something you want me to answer. Sure.
On this, this is like back in like SN1 reactions.
Okay.
It says that exception, primary carbocation rule of not forming. Why is it not really form in like a benzene?
Oh, that was good stuff. Yeah.
Yeah. Why does that not work? Because I feel like that's always a big like secondary. I don't know. There's always something in there.
Wait, why does what not work?
Why is there exception to the primary carbocation in the benzoic position?
Sure. Yeah, so.
I just don't really understand.
Yeah, no problem. Okay. We said that the best type of carbocation is a tertiary carbocation. That's more stable than a secondary carbocation, which is more stable, and really it doesn't exist. A primary carbocation. Oh. Primary carbocation. Okay. And I didn't go as much as I normally go into the explanation of why this trend for, part of it has to do with, and forgive my anthropomorphizing here, you guys remember what that means, right? So if you have a tertiary carbocation, if you have it surrounded by carbons, right? You've got it surrounded by 3 carbons, that's why it's tertiary. A carbon-to-carbon bond can essentially say, oh, you have a positive charge on you? Well, we're sharing this electron pair. That's our bond, okay? But you know what? You've got a positive charge on you. You're super unstable. I can loan you some of that electron density. I can, through our sigma bond, okay, I can loan you some of the electron density. So essentially, in a carbocation, we never really draw it like this, but these become very polarized bonds, okay? Does that make sense? Okay. A carbon bond is able to do that. A carbon-hydrogen bond, hydrogen can't give it up. For lack of, without, it just can't. Okay. That's the only electrons it has. Okay. That bond just isn't a polarizable bond. Hydrogen can't loan any density to help out. Okay. So a primary carbocation would have only one other carbon to try to help him out with that positive charge on there, and 3 hydrogens that can't do anything for him. Tertiary carbocation can, okay? So that leaves that there's no way to stabilize that carbocation, okay? So now those all make perfect sense, yeah? Okay. So why is that okay? That's a primary carbocation.
Resonance.
Resonance, yeah, that's a showing question.
Yeah.
I mean, so maybe you're like, well, why does the resonance help? It's a matter of, we got to find some strategy to stabilize that positive charge. And one way is to spread it around among a bunch of different carbons, so it's not localized just on one carbon. So, Video's still going, okay. All right. And then you can get another residence structure possible. Okay, and then one last one possible.
And those can be nucleophiles then? Or not
Carbocations are never nuclear.
No, I mean, yeah, but they can proceed in like an.
They could do, what I think you're getting at is, they could do SN1 chemistry.
Yeah,
They could even do well, they can't do E1. Because you can't do it in a limit, there's no beta, there's no adjacent H's. Okay, but they can do SN1 reactions.
Okay. In all positions?
Oh, that's an excellent question. No. Yes, all, none of these is the correct residence structure. Okay. They, you have a residence hybrid that has partial positive character there, partial positive character there, partial positive character there, and partial positive character there. Okay. But if a nucleophile reacted with the hybrid of all that junk, it would only react there.
Okay.
Why is that?
Farthest, most.
No.
No.
Any thoughts?
It's the, it's the wrench that can,
I see your point, that it is the most sort of sterically available, but that's not really the phenomenon here. So imagine, what's our nucleophile? What do you guys want? Let's say, how about cyanide? That's a good non-nucleophilic base, great SN1 type of nucleophile. Okay, so it'll attack there, and think about that product you get. Well, let's draw it actually. You get that product, and you wouldn't see the product if it attacked there, or if it attacked there, or even though there is some partial positive character there. Guys, were you hatching a plan as to why?
yes and no. I
Okay.
just was trying to figure out what, if it was the nucleophile that attached to the positive, like I know it's the electrons that attach to the positive charge, but it's like the nucleophile or the nucleophile.
It's the electrons of the nucleophile.
Yeah, but like the group of where the electrons come from, like where the electrons are attached to on the other side is the nucleophile, right? Like
Which atom is the nucleophile? Is that what you mean?
I get it. I got it.
Okay, good. I don't know. On cyanide, it's kind of weird because there actually is a lone pair there, but that's the reactive lone pair. There are extraordinary conditions where you can get that to react, but more typically that is the electron pair that reacts. Okay, that will create a neutral product. This would not create. Well, it would be the formal charges.
Benzene rings are really strong, so they wouldn't attack.
Stable.
any of the- Yeah.
Stable. You regenerate this aromatic ring, this alternating double bond all the way around if you attack there. Okay. If you attack here, then you disturb this alternating benzene ring structure. Okay. We didn't really go into do an elaborate talk about aromaticity, but alternating double bonds around a ring is called aromaticity. Has to have an odd number of pairs of pi electrons, so we've got 3 pairs of pi electrons. And it has to be cyclic, and there's some other requirements to be aromatic, but benzene definitely fits the bill, and that's the only place you attack where you get to retain that structure. Anything else? Okay, can I do something with it?
Yes.
draw the products.
Could you draw the structure to the MCPBA?
You want me to draw that out?
Yeah.
Sure. These are all MCPBA. This is the one that we just did. All the varieties. Draw on the products to that.
Thank you.
Well, I don't have any, there's no water. So, yeah, so your hydroxide, so just that, dude. Oh, it's so funny. I trained you guys. There's no, remember, we don't have the second step. All the MCPBA does is make epoxides, okay? So this is kind of what I'm talking about in terms of, let's learn the core change you have to make in the molecule. And that core change, okay, for an MCPBA reaction, you have to find the double bond. You got to take away one of the bonds, the pi bond, And then you gotta replace it with an oxygen 2 bonds. That's it, that's all you have to do. Julia nailed it.
I did not nail it.
It's okay, you did well on the test. Let off a stream of profanities, the likes of which my poor ears, my delicate ears. Yes.
I wasn't
Yes.
as bad as Ralphie Parker's father.
You what?
I was not as bad as Ralphie
I haven't
Parker's father.
gotten to last.
Not as bad as not.
Ralphie Parker's father? That's the movie you're referencing.
Right.
And I'm not as bad as his father.
Right. I am inadvertently
With
referencing
this
that.
one, you would take out this bond and then you just add.
Yes,
the other.
ma'am. That's it. That's all it is. Yes. Yes. Yeah. Yeah. I mean, you know, and by the way, when, at least in my class, when I'm giving partial credit, that's most of the credit. Now you gotta fill in the other junk, you know, you can't just, you don't wanna just leave this three atom product, you want the other stuff, yeah, you want, so, you know, right here you go, okay, double bond's gone. And we get that 3-membered ring.
That's all it is.
That's all it is.
Happy birthday.
Hi, oh, thank you.
You're welcome.
Are you gonna take this final again?
I don't think
You
so.
were a glutton for punishment. Pass this
Hey, I
time,
had a lot of fun with this final, I don't know what you were talking about.
right?
I never thought that it would be simple.
Can I take this one instead of something?
Yes.
I think we ever-
Absolutely.
I don't think I ever.
Absolutely. You're probably gonna fail Selamolek if you do that, but I'd love to have you in there.
Well, can it like substitute?
Oh, I had no idea.
They work out.
Yeah, it's like same thing.
Different times, so different times. You can do them.
Yeah, probably. Who do you have Selamolek with?
Jensen?
Jensen? She's one of my moms.
I know,
Yeah, that
I
one.
wasn't sure, but I mean, that's for
Is that her over there? Oh. She doing a review session too?
I know, I was like, oh, I guess it makes sense to really work.
Yeah.
No, I'm serious. So we're actually working on
Yes, ma'am.
So it looks like the one of the far right on the bottom,
Yeah.
that oxygen is sitting inside of the left ring.
In reality,
Or is it sitting on the?
yeah, it'd be really cool actually. This would be, in this, okay, starting material. In this region of the starting material, it would be fairly flat, okay? The others would be a little bit twisted. You know, this can't quite make a chair configuration, but it would be a little bit twisted and everything like that. But right here, this is all flat, okay? Because it's SP2. When the epoxide comes, in a sense, it would remain fairly flat. And the oxygen would actually be sitting right here. Okay, but that's just hard to draw.
Okay, but
Okay.
having the thicker triangle.
Yeah,
would make-
yeah.
okay.
Now, you could, the epoxide could come from either side. It could come from this side or it can come from the other room, yeah? Okay, should I draw both products? Why not? Yes, thank you. Maybe, did you know that? Because you knew that, or because I'm a broken record and I always play that trick? Okay.
I think I knew that.
Okay, good.
Yeah.
Because there's a plane of symmetry, yeah? We're right down the center. Yeah, I didn't mean to insult you, but I mean, like, anyway. You know what I'm gonna say. But on all these others, in actuality, yeah, and I probably would ding you. What I would do if it was 12 points, I would give you, you know, a bunch of the points, the majority of the points for one of them. If it creates a chiral compound, so this is a chiral compound. Okay. then you get the other one there. You wouldn't get it, you'd only have one here, okay? Because you're not creating a chiral compound, you're not creating chiral centers, okay? This isn't a chiral compound, okay? This is not a chiral compound, so actually the only one that's chiral where you get to is that one, okay?
Do the steps on that top one, is it just that, like the gate swings open, gets the OH, and then the H is pulled off, leaving electrons that connect to the other C?
Say it one more time.
Like, so you have your double bond, and then the gate swings open,
Yep.
attacking the OH,
Uh-huh.
it pulls the OH off, and then the the OH is deprotonated, leaving electrons on the oxygen, which connect to the other C.
Kind of. That's a good hypothesis. If you had never seen the that would be a good way. It attacks that oxygen, okay? When it attacks that oxygen, it kicks these electrons off, okay? I'll actually draw it out. It's actually probably easiest if I just draw this mechanism here, actually. So. Okay, and then, you got your benzene ring here with your chloride. Chlorine. Okay. So the double bond, the gate swings open. Okay, that kicks these electrons here, which kicks these electrons up here to grab that H.
Oh,
And then these electrons go back down to that carbon.
okay.
Does that make sense? So when the gate swings here, okay, it swings open, boom, there's one of the two bonds that have to be made to that oxygen. And then those last electrons coming down, that's the second bond to that oxygen. Okay. I'm trying to wrap my head around and figure out from a teacher standpoint, like why things like this stump you. Is it just I didn't have the time to really learn that MCPBA reaction? Or is there another way I could be delivering it to you?
I think it was just the fact that every reaction kind of does something completely different from the others, and it's very hard to find the epoxidants if you don't quite remember. Find the
Like the
The
distinguishing
trend,
factor.
trend,
Yeah.
pattern or something.
Right.
Right.
Trying to find the pattern,
Right,
because I'm
right.
sure.
If you don't know what to look for, it's hard to find the pattern that happens
Right.
from the equation to equation.
I couldn't read my notes.
What's that?
And I couldn't read my notes for those.
Oh, man.
Are there other things like MCPBA that would make an epoxide?
There are. That's a great question, and that was another problem on your exam. Is that why you asked? Because that's one of the other, yeah. Okay. And this was in the section where we talked about ether formation, specifically how you make epoxides. I taught you that if you have an OH on one carbon and on an adjacent carbon you have a leaving group, like a halogen, okay, bromide or chloride or a tosylate. If you then treat the OH with a base, and we almost always use sodium hydride or potassium hydride. That's the main purpose in life for potassium hydride and sodium hydride. Okay? That you create an epoxide. The way that works, we just, we're sort of concentrating on what the product is, but well, how does that work? Well, the hydride comes in and grabs that proton, kicks those electrons off on that oxygen. Okay. And then it's sort of just in perfect, in the perfect location to be able to do that SN2 reaction. Okay. And so you get an epoxide. Okay. So, I mean, you do have to really know these things cold, so that if you see an OH with an adjacent carbon, okay, that has a leaving group, and then you see a hydride, aha, the leaving group will be gone, and the OH will have formed an epoxide with that carbon, okay? So you just have to look for, where's that carbon with the leaving group, get rid of the leaving group, and then draw a three-membered ring epoxide in that range. Okay, that doesn't totally answer that question that you're referring to, because there was one little tricky trick. Okay, we'll get to the tricky trick in a second. Okay, let's do something. It's really hard sometimes generating examples in your brain sometimes. I don't know why. Cyclic ether. This one's and there's something a little tricky with that one. What?
My stomach is making such weird noises.
There's cookies over there.
No, I'm not even hungry.
Oh, okay.
I don't know what's wrong with me. Yeah, I guess so. It's yelling at me for eating. Oh, yeah. Yeah.
Hi, yes.
Is a good way to study like chapter 9 and chapter 12, just looking at the reagents and what they're forming, so like NaH or KH forms and oxides. Or like, do you kind of have to look at the substrate too? Like that's what I struggled with in the last exam, was like how to study, like I tried to study like an example.
I have the straw. I like the straw.
Yeah, I think reagents is a good thing to study, but you can't ignore the substrate.
Yeah.
Because back in when we were doing SN1 and SN2 and stuff like that, the same reagent can give you a different reaction depending on what that starting material is, right?
Yeah.
Yeah, because like
What?
put ice in it, like I can put ice in it like in the morning and it will last.
Yeah,
for, like,
I don't know, it's hard. I like, as I've mentioned, I like note cards a lot.
One that's staying in plastic zone,
You know, this is kind of a tough point to go and make note cards. You probably got other
I
tests.
made some note cards from the last exam, but again, I tried to make like examples rather than.
And that's interesting. That's how I would do it too. Is I would use specific examples, but that doesn't seem the way to be the preference of most students.
Yeah.
What most students seem to like is R groups. They like
Yeah.
learning reactions with R groups. And maybe that does make a little bit more
I think because
logical.
I was just focusing on like what that specific example was, rather
Oh
than
yeah,
the
and I see.
whole
I think that
big
is one thing that really
picture,
trips
and
students
that's
up.
what- Yeah, that's
It's-
what we got.
I don't think I've ever done it. If I've done it by accident, where I use the exact same example.
Yeah.
I think that's one of the, I get a little bit of that hurdle to achieve OCHEM is being able to generalize it. Yeah, you learn it in one context, but now you need to apply it in different contexts. So I think if you can, we haven't learned that many reactions, so if you can try to do it with our groups and create note cards, and like I'm always, preaching like I'm your parents, it's none of my business, but, just work quickly. Like really say, you know what, I'm gonna do these note cards, I'm gonna burn through this, and I'm giving myself an hour and a half. That's something that I recently started in my own life, my own work, is doing that maybe 2-3 years ago. I started doing that. And I think what helps me is I used to be in construction. And when you're in construction, do you think you've had bad bosses?
No.
In construction, bad bosses are like some guy, be sober, may not be sober, who's like red in the face, like cussing you out. Are you hurt? Are you hurt? Why?
What were you doing then? Because they only do that if you've done something where like you kind of
That is
deserve
so
that.
unfair.
You deserve that. So what did you do?
Exactly,
What did you
Andrea.
do?
How much construction experience have you done?
My dad's been on construction sites for a very long time. So he's done that for a while, and he's been a manager for a long time, and he has friends who have their
You ask him if
licenses
I'm lying. You ask him if I'm lying. The key difference is that I worked for guys, small operations, and so it was his money. You know what I
Yeah.
mean? So,
Yeah.
If you work for a big union kid,
doesn't
your
matter.
boss,
Yeah.
hey, try to work a little faster.
But
But if
see,
it's
if you
you're standing
get
next to
caught
the dude
yourself-
and you take 3 hours to install that door when he thinks it should take an hour,
Well,
he just lost $50. I mean, there's little dollar signs that are,
Yeah.
and there's 4 slow ass idiots
I thought you meant like if you
wandering
really
around
caught
like,
yourself.
oh, I put in the door wrong. Yeah, I mean, it's frustrating.
And then
so-
if you're like
anyway.
cutting your toe, then like yeah, of course he'd be angry with you for like cutting that, getting really hurt, because then he has to pay for that. So
I did. One of my first bosses, a drinking problem, and he was missing a leg. And so, bless his heart, that's a terrible thing, But he was so scary, and he would come hauling after me with this leg. It was like something out of a bad movie. Anyway,
terrible.
yeah. Okay, how are we doing? Back to work. Oh gosh, I just realized all that's going on YouTube. There's some way I can just make it so certain people can say, I don't even. I'm not even gonna bother. That's great. I'd love to get the right stereochemistry. If I indicate stereochemistry with my starting materials, chances are you need to put stereochemistry in your product. That's a good little rule of thumb. It's probably not perfect, but I bet 9.5 times out of 10, that's the case. Okay? Ma'am.
Sorry, I didn't-
No, that's okay.
But this last one, is that the thing where they're on the same side?
Exactly. And that's why, that was, when I make a test, I always want, 1/3 cream puffs 1/3 reasonable questions, and 1/3 kind of challenging questions, and that was one of the more challenging questions.
So what would we do?
That's no reaction. That was the no reaction. You know how I said in the instructions it would be, and nobody got that. Oh, no, that wasn't the no reaction. It's a total lie. That's a total lie. But this one would be no reaction.
Because they're cis to each other.
They're cis to each other, you can't do it. Because it's an SN2 reaction, okay? And this is not going to be able to attack that carbon with backside attack, okay? It's not going to be able to, like, you know, bend around and create this incredibly strained thing. Does that make sense, intuitive? Yeah. Okay. All right, so let's do this guy here. And again, now I'm sort of getting a little bit into the nuances. I'm going to do the stereochemistry of the product. If you had just written the epoxide there, you'd get at least 8 out of 12 points. I mean, you do well on the exam if you went through it like that. Okay, but we want A's. Okay, according to my starting material, if that's the starting material I start with, how should I'm going to draw a 3-membered ring in between these carbons, yeah? Okay. And where should the oxygen be? In our room or in the room next door?
Both.
No, it wouldn't be both. It wouldn't be both. Because in this case, you get situations where it's both, where the starting material doesn't have a chiral center, and in the process you create a chiral center. That's when you can get both. Okay? Here, we're starting with a specific stereochemistry. Okay? So, well, think about the mechanism. Okay? It's backside attack. So you get inversion of configuration at the carbon that had the leaving group, right? You get inversion of configuration at that carbon. Okay. So this is the carbon with the leaving group. You're going to get inversion of configuration at that carbon. Okay. So which room should the oxygen be in? Our room or this room? Yeah, exactly. You can also just sort of think of the mechanism. This is going to be O minus, and then the oxygen's going to go attack that carbon. But nothing's going to happen at that carbon. That carbon is just kind of along for the ride. Okay? So it would be impossible actually to get the one where it's coming from the other side of the room.
So really, you're just taking the stereochemistry of the OH, whatever that is. It's supposed to be.
From now on, you just get the stereochemistry of the OH. Wacky how you can teach this stuff for 6 years and not say it like that. Well, if you want to put it simply and straightforward, I suppose you could describe it that way. All right, this guy here, we get rid of the leaving group, we make an epoxide. Which room is the?
Ours.
Our room.
Yeah, like that's the pattern.
Yeah.
What if I told you it doesn't matter?
Then you'd be right.
Because if you decided to draw the other one, you're drawing the same thing.
But
That's kind of a cool one. That's one where your starting material is actually chiral and it loses chirality in the reaction. That's kind of cool. You're not going to see that very often.
But it would not be correct to make them just straight lines, correct?
You could actually. I would accept that. In the convention, by organic chemistry convention, that's okay.
Okay.
And here I haven't indicated any stereochemistry, so neither do you have to. Oops, CH. Okay. How about this guy? What room?
The other one.
No. Okay. And then that's no reaction. Ma'am.
You just said this was no reaction, and you marked
No,
it
no, no.
opposite.
That is no reaction.
But is this one?
That's not no
Oh.
reaction. And then and
Why?
So why?
Yeah.
Because it has NaH and OH. and that
Essentially
means-
because the OH in that case had 2 to choose from.
What?
Oh,
Let me
so
see the
choose
problem.
other.
Does anybody have it in front of them?
I get it.
Because there's two.
Okay,
This is
so
the other.
right here. Hopefully
Right?
not.
I like this game.
Okay.
I'm losing this game.
So this gets, oh yeah, you bet it. This gets deprotonated, yeah?
Yeah.
What time is it? This gets deprotonated, and then, yes, it would be no reaction, it can't react with that carbon, but this one isn't in the right orientation.
So if the other CL wasn't there, then it would have been no reaction.
If that seat,
Yeah.
that would have been no reaction.
Yeah. Okay.
Okay, I guess I don't understand why we can't put both for, like,
Oh,
this way.
well, okay, so you want to put,
Yeah, I'm sure this year it'll be bigger. Like, there's gonna be more people on the team, and last year was our first year.
you want to put that guy, yeah? For that one there?
Jay, do you want to put it?
How, how could this guy, in order for this starting material to do that, you'd have to get inversion at that carbon. You've got to somehow change that carbon to sticking out at you. I'm not explaining that well. I'm not, no, I'm failing you. I apologize. I will return some of your tuition. Not a dime.
Why are the products not the same thing? Why is it not the same?
Because the double bond.
Okay.
There's no planar symmetry, right? Or no, that's a bad answer to your question. A better answer to your question is try to superimpose them. That is the ultimate test of are they the same thing, and you can't superimpose those.
Okay.
This, if we draw this guy, those are superimposable. It's just pancakes.